Have you ever looked at something just incredibly complex and you've wondered, is there some secret unifying principle behind how it all works, how it all hangs together? Well, today we're diving into a concept that
Called spectral redundancy. And it really is this profound mathematical idea.
our mission today is to unpack this concept. We want to explore how spectral redundancy shows up, across quantum physics, AI, big infrastructure projects, even biology.
We'll look at what it means for how we understand these systems, sure, but also maybe the very limits of what we can know.
The limits of knowledge itself, spectral redundancy. What is it really?
Spectral redundancy describes a system's core, its fundamental modes.
Modes.
Think about any complex system, right? A neural network, a transport grid, maybe a quantum computer.
Yeah.
We can describe each of them mathematically. We use something called a governing operator. It's like the master equation or the blueprint for that system.
Different systems have different blueprints, different operators.
Exactly. For networks, like transport grids, it might be something called a graph. It maps out connections. For AI, especially neural networks, you might hear about the neural tangent kernel, or NTK. That helps describe how it learns.
Okay.
For quantum systems, it's usually the Hamiltonian that defines its energy states.
These operators capture the essence of the system mathematically. Where does the spectral part come in?
Right. Spectral refers to the analysis of these operators. Specifically, we look at their eigenvalues.
Eigenvalues. Okay, sounds technical. What are they, intuitively?
Think of them as the system's natural frequencies or its fundamental patterns of behavior. Imagine a guitar string. It has its main note, but also those overtones.
Harmonics.
Eigenvalues are inherent ways the system can vibrate or operate or exist. It's natural modes.
Where's the redundancy?
Redundancy happens when these modes start to cluster. Sometimes they even repeat exactly.
Cluster. Bunch up.
This isn't just a numerical fluke. It tells you something important about the system's design. The system has multiple ways, slightly different, but functionally the same to achieve the same result.
Like taking different streets to get to the same place.
Exactly like that. Think of that Tokyo map again. So many routes between 2 points. Some might be slightly faster, some slightly different scenery, but they get you there. That multiplicity, that flexibility, that spectral redundancy.
Built-in options. Leeway.
That's a great way to put it.
You mentioned it's kind of a double-edged sword.
It absolutely is. And this is where it gets really, really interesting. This redundancy creates this powerful duality, two sides of the same coin.
Lay it out for us. Side one.
Side one is robustness, incredible resilience. When those eigenvalues cluster, it's like the system has built-in shock absorbers, local damage, failures, minor glitches get absorbed, they dissipate. Why? Because multiple internal states can lead to the same observable outcome.
From the outside, it looks like it's still working fine, even if something's broken inside.
Think about traffic rerouting automatically when a metro line gets cut. The system adapts. It finds another one of those equivalent pathways. The overall function getting people where they need to go continues with slight degradation, not a catastrophic failure. That's robustness, driven by spectral redundancy.
What's the downside?
The other side is computational hardness. The multiplicity that gives you robustness makes it incredibly difficult, often computationally intractable, to figure out the system's exact internal state from the outside.
Wait, so you can see what it does, but you can't know how it's doing it.
Exactly. You can observe the output, the behavior perfectly, but reverse engineering the precise internal configuration becomes incredibly hard, if not impossible. We call this local spectral indistinguishability. Many different internal setups can look identical from a local or external viewpoint.
The thing that makes it tough also makes it mysterious, like a black box.
That's the core paradox.
Yeah.
Precisely. Robustness seems to come inherently bundled with a degree of inscrutability.
Systems that hit this sweet spot, this Goldilocks zone of redundancy. Not too little, not too much.
The systems are super resilient and fundamentally hard to analyze completely, maybe even cryptographically secure because their internal state is so hard to determine.
Okay, this is starting to paint a really interesting picture. It's not just abstract math now. Let's talk evidence. Where do we actually see this playing out? Metros.
Researchers looked at real-world metro systems and found that networks with optimal spectral redundancy, distributed connections, adaptive ways to heal, showed near-perfect survival rates under severe simulated attacks, like reporting 0 permanent losses. The system just gracefully degrades finds alternative.
The Tokyo Metro is a prime example, even though it looks like chaos on the map.
Tokyo Metro seems chaotic, but it's spectrally optimized. Stations and lines create eigenvalue clusters, tons of routing options. If there's an incident, traffic gets rerouted almost instantly. The redundancy absorbs the shock. That's real-world robustness from this mathematical principle.
What about AI? You mentioned Peterson graphs.
Oh, yes, the Peterson graph neural networks. This was a fascinating experiment. They built neural networks using the structure of the Peterson graph. The Peterson graph is famous in math circles for having almost perfect spectral properties. It has a maximal spectral gap.
Maximal spectral gap, meaning the modes are nicely spread out.
Think of it as optimal spacing between those fundamental frequencies. It allows for really stable and efficient information flow, like a perfectly tuned instrument.
How did these networks perform?
They showed significantly better performance on tasks like regression. They maintained high accuracy even when researchers cut half of their internal connections, 50%.
50%, wow.
Because the Peterson graph structure distributes eigenvalues optimally. It creates efficient pathways for learning gradients to flow. If you damage one path, others seamlessly compensate. It's the same principle as the metro rerouting, just happening inside an AI. Robustness through redundancy.
From AI to quantum labs, how does spectral redundancy help?
Imagine you have 50 quantum labs around the world, running sensitive experiments, building quantum annealers. They need to prove they're running the same experiment, getting the same quantum state, but without revealing their secret internal designs, their proprietary qubit couplings.
That sounds impossible, with quantum stuff being so finicky.
It's a challenge because quantum annealers are complex graphs. The eigenvalues of their graphlet encode the quantum state. Tiny temperature fluctuations in each lab impossible to avoid completely would make the raw eigenvalue fingerprints look different, even if the underlying quantum state was identical.
Comparing them directly wouldn't work.
The solution is incredibly elegant. It involves applying a special mathematical function, the Lambert W function, to those eigenvalues along with a temperature correction.
Lambert W function. Why that function?
Because of the underlying physics. Real quantum systems naturally produce eigenvalue distributions that follow a specific pattern called Gaussian unitary ensemble statistics, or GU. A key feature of G is that eigenvalues tend to repel each other. They maintain a certain spacing.
Okay, quantum eigenvalues repel. What about non-quantum systems?
Classical systems trying to fake quantum behavior produce Poisson statistics. Eigenvalues are more randomly scattered, no repulsion.
I see the difference. The Lambert W.
The magic of the Lambert W function is that it creates a signature that's invariant to temperature changes while preserving those crucial GUEs. It keeps the quantum repulsion pattern intact. It cleans up the temperature noise but keeps the essential quantumness of the signal so labs can compare results reliably.
And securely. They don't want to reveal secrets.
Exactly. And here's the other beautiful part. Trying to reverse engineer the original quantum setup, the qubit couplings from these Lambert W transformed eigenvalues, that's an NP hard problem.
Meaning computationally infeasible, basically impossible for current computers.
It provides cryptographic security. Changing one tiny coupling in a small quantum system changed the final Lambert W fingerprint. Super sensitive tamper detection.
Wow. They can prove they're identical without showing blueprints. Clever.
Clever. It's using quantum spectral statistics for verification.
Okay, we've gone from metros to AI to quantum labs. What about space?
Recent research is formalizing something called spectrally redundant calibration for radio interferometers.
Huge telescope arrays.
Exactly, like the ones mapping the early universe. They use this method, which involves repeatedly sampling the same cosmic signals through slightly different parts of the array. This builds in redundancy, making the whole array much more robust to local errors like a faulty antenna or atmospheric disturbance. The scientific measurement stays stable.
Redundancy helps telescopes see clearer.
It helps maintain calibration accuracy despite noise and errors. The calibration process itself remains computationally manageable. Redundancy for robustness.
Okay, one more AI example because it's such a hot topic. Large language models, LLMs. You mentioned Solora.
Right, spectral encoding, low-rank adaptation, or SOLORA. A recent paper showed they could fine-tune LLMs while turning off pruning up to 60% of the model's parameters.
60%, huge chunk of the model gone.
Massive. Yet the models maintained their performance levels, which is a stunning demonstration of just how much parameter redundancy exists in these huge models. They're incredibly robust to the damage. The spectral encoding part makes it harder to figure out the model's exact global state by observing its behavior, tying back to computational hardness.
It suggests there's an optimal level of sparsity, a Goldilocks zone for LLM efficiency.
It echoes what we see in other domains. Finding that sweet spot between complexity, efficiency, and robustness. Solora is one way to potentially engineer systems closer to that zone.
This Goldilocks zone idea seems central, linked not just to robustness, but maybe even to intelligence itself.
That's what some fascinating research suggests. Intelligence doesn't just pop out of any complex system. It seems to emerge specifically at a critical point of balance, sometimes called the edge of chaos.
The edge of chaos, SAT problem you mentioned, the logic puzzle.
Exactly, the Boolean satisfiability problem. As you tweak the ratio of constraints to variables, the problems go from easy to super hard, then impossible. Right at that transition point, around a ratio of 4.26, that's where the hardest solvable problems live. Solving those requires what looks a lot like intelligence.
And the connection is.
When you look at the structure of those hard SAT problems, their underlying graphs exhibit optimal spectral redundancy. Enough pathways to search for a solution robustly, but not so many that it's trivial or chaotic. It's that balanced redundancy that seems to create the conditions where intelligent problem-solving becomes necessary.
The structure demands intelligence.
That's wild. What about that Yale study with cellular automata?
Yes, elementary cellular automata, ECAs. Simple grids, simple rules, but they can generate incredibly complex, unpredictable patterns. Think Rule 30 or Rule 110. The Yale researchers trained LLMs on the outputs of these different ECA rules and found something striking. The LLMs trained on the complex edge-of-chaos rules developed significantly greater reasoning abilities. They became smarter just by learning to predict these patterns.
Yes. The training data doesn't need to be inherently intelligent. It just needs to be sufficiently complex to have that right kind of spectral structure. The LLM, by grappling with the inherent spectral redundancy of Rule 110, for instance, learns sophisticated pattern recognition. It builds internal models. Intelligence emerges as a byproduct of mastering that complexity.
The complexity is the teacher.
The structure of the information shapes the intelligence that processes it.
This leads to something really mind-bending you mentioned earlier from your own work, that emergence isn't just about the system, but about us, the observer.
This was a real head-scratcher for us initially. We were doing these experiments, perturbing systems, measuring sensitivity, and we kept seeing this weird scaling law, NDMAR 0.753. It felt too specific to be random.
Universal signature.
Exactly. As we dug into it, the shocking conclusion we reached was that emergence, it's not just intrinsic to the system, it's observer-dependent. That scaling law wasn't just about the system's physics, it was deeply intertwined with how we were measuring the physics.
How can that be? How does the observer change the system's properties?
Think about any observer, a scientist, an instrument, an algorithm. They have limits, right? A certain resolution, an integration window, how much they average over time or space, a limited information budget. These actively shape what the observer perceives. Our measurements aren't a perfect window onto reality. They're a filtered, processed version. And that filtering can create or reveal emergent properties.
How we look determines what we see as emergent.
Yes. We found there's an optimal Goldilocks observational scale, LN, which grows with the system size n, roughly as n.1. Counterintuitively, coarser observers, looking with less detail, averaging more, are better at spotting emergence in larger systems.
More detail isn't better.
Not always. Not for seeing certain kinds of emergence in large systems. This explains why the threshold to see a response threshold decreases with size. It's not just the system getting more sensitive, it's that our view reveals that sensitivity more easily.
Okay, observation matters. But then you found something even stranger about gap collapse.
Yes. This was the twist. Our models assumed perturbations get amplified, causing emergence. That happens, but it wasn't the main story. The data showed the spectral gaps, the spacing between those fundamental nodes, were collapsing incredibly fast as the system size grew, way faster than we thought.
Meaning the modes are becoming indistinguishable.
Exactly. Maybe emergence isn't just observer-dependent, maybe it's actually observer-created. The act of measuring at that Goldilocks scale, where the gaps collapse from our perspective, brings the emergent behavior into existence for that observer.
Spectral redundancy shifts from being a property of the system,
being fundamentally a property of measurement theory itself. How we measure defines the redundancy we perceive and thus the emergence we observe. It's a huge shift.
Facing these kinds of results, you decided to really rigorously test your initial ideas, the three horsemen.
We had to. Science demands honesty. We ran extensive Monte Carlo simulations, thousands of random trials to see if these ideas held up statistically.
What did you find? Horseman #2, redundant spectral modes clustering.
That one passed with flying colors, 99.5% success rate in simulations. Confirmed our intuition. Spectral redundancy is mathematically inevitable when you build systems from modular parts. The universe has no choice but to create it.
Okay. Inevitable redundancy. Horseman #3, selective symmetry breaking, the system choosing a direction.
It's parameter dependent. It needs a perturbation strength above about 0.2.
Below 0.2, not much.
Weak effect, low success rate. But above 0.2, strong effect, 44-75% success rate. Genuine critical point, like a phase transition in physics.
So it happens if the conditions are right.
And we confirmed scaling effects. Larger systems, like 5x5 matrices, showed stronger effects than smaller ones, suggesting size matters for complexity emergence. Maybe there's a threshold.
Refining the claims. What's the takeaway?
Our strong, statistically solid claim is modular composition produces spectral redundancy. Our conditional claim is strong symmetry breaking produces direction selection. Our hypothesis, supported but needing more work, is larger systems exhibit stronger complexity emergence effects. It's a precise picture, grounded in data.
You mentioned this inevitability can be shown with a simple example, just two tiny matrices.
Exactly. To really drive home that this isn't some complex engineered feature, but a basic mathematical fact, we boiled it down to the minimum. Imagine two tiny patches, A and B, represented by 2x2 matrices. Let's say they have similar eigenvalues, like 1.1, 0.9, just local pieces of information.
Okay, two patches.
Now you compose them categorically. In the simple case, it just means multiplying the matrices. And watch what happens to the combined eigenvalues. They automatically cluster perfectly. In our example, they become 0.99, 0.99. It's an automatic consequence of multiplying matrices with similar initial eigenvalues.
No design needed, just clusters.
It just clusters. If you keep composing, adding more patches, the clustering gets even stronger. The system drives itself towards redundancy. This clustering is largely preserved, even if you use different glue-on symmetry operations like permutations or reflections to connect the patches. Non-identity glues can break the perfect redundancy slightly.
This tiny example shows redundancy isn't engineered, it's baked into the math.
Absolutely. It's a direct consequence of deeper mathematical structures. Things like descent theory, how local pieces glue together globally, stack geometry, how symmetries affect structures, even higher category theory, the abstract language of composition itself.
Connects to fundamental math.
Think of it like Ramsey theory in combinatorics. Ramsey theory guarantees certain patterns must emerge in large enough random structures. Similarly, these categorical laws guarantee spectral redundancy must emerge in any sufficiently structured system built from parts.
So the killer line is, spectral redundancy isn't engineered, it's mathematically inevitable.
That's the core takeaway. Quantum systems, neural networks, biology, maybe consciousness all involve this modular categorical composition.
Distinguishing what's inevitable from what's enabled.
What's inevitable by mathematical necessity is this. You take local pieces, you have rules for gluing them together that allow some flexibility or symmetry. You will get spectral redundancy. And that redundancy forces robustness and computational hardness. That's how physics and math work when building complex things.
Okay, inevitability leads to redundancy, which leads to robustness.
Right. Now, that robustness and hardness creates a fertile ground, a necessary substrate for intelligence. Systems that can resist noise, adapt, and perform complex computations are likely to exhibit intelligent behavior.
Intelligence itself isn't guaranteed.
Correct. The universe has to create the conditions for intelligence, the robust, computationally capable substrate. That's the inevitable part. But whether intelligence emerges depends on other factors. Selection pressures like evolution, learning algorithms like gradient descent, energy flows like in thermodynamics. Those are dynamic processes that act on the substrate.
The universe is biased towards intelligence, structurally.
It's structurally biased. It provides the stage and props. But the play of intelligence needs actors and a director, those dynamic forces. It's more profound than saying intelligence is inevitable everywhere.
If systems are inevitably redundant and hard to know, that leads to this idea of an epistemic ceiling, a limit on knowledge.
Spectral redundancy implies a fundamental limit on what any observer can ever truly know about the exact internal state of a system. It's not just about lacking data or tools, it's a structural impossibility baked into the system's nature.
And ambiguity.
Many different internal configurations, microstates, network architectures, physical geometries can project the exact same observable behavior or summary statistics. You end up with an irreducible equivalence class of explanations, a whole set of possible truths that all look identical from the outside.
That's shocking because we usually think, get a better microscope, measure more precise.
Our intuition tells us more data solves ambiguity. Spectral redundancy says not always. For systems in this regime, some ambiguity is fundamental and cannot be resolved by simply refining the same kind of measurement.
You can have two different AIs with different internal wiring
that perform identically on tests. You couldn't tell them apart by observing behavior. Their internal differences are hidden behind spectral redundancy.
And the tools we use rely on redundancy for robustness.
Yeah.
Contribute to this.
An instrument designed to be robust by exploiting redundancy will be fundamentally ambiguous about the precise cause. Enabling robustness imposes the epistemic limit.
Where else do we see this ceiling? You mentioned examples.
Once you know what to look for. In theoretical physics, the ASCFT correspondence has this puzzle. Many different bulk spacetime geometries can map to the same boundary data. That's an epistemic ceiling. In radio interferometry, redundant calibration makes the telescope robust, but it also hides certain types of instrument errors from the spectral probe. They become invisible.
And the LLM pruning.
A perfect example. Removing 60% of parameters yields functionally identical models. Performance doesn't reveal huge internal differences. The equivalence class is massive. Even in basic network science, different graph structures can have the same spectrum. You can't perfectly reconstruct the network just by listening to its vibrations.
Redundancy is good, but it hides things.
It's celebrated as a feature for robustness or efficiency, but it simultaneously imposes this fundamental limit on knowledge. It's a deep trade-off.
What are the implications of accepting this limit for technology?
Huge implications. For science, some debates might be fundamentally undecidable based on available observation types. We might need radically different probes, not just better versions of the same ones. For instrument design, it pushes towards diversifying how we measure, not just how accurately. For security and privacy, it enables plausible deniability. For AI safety and interpretability, it's a massive challenge. Behavioral tests alone are insufficient if vastly different internal states can produce the same behavior.
We need ways to peek behind the veil.
We need to learn to work effectively within the constraints of that veil.
Can we engineer with it? Can we design systems in that Goldilocks zone?
That's the next frontier, spectral engineering. And there are frameworks emerging to help do just that. One promising approach is nutrisophic goal programming, or NGP. NGP helps balance competing goals we always face. Truth, like performance, accuracy, indeterminacy, flexibility, adaptability related to redundancy, and falsity, robustness, security handling errors or attacks.
Balancing truth, indeterminacy, and falsity. How does it work?
It's a mathematical optimization technique. Researchers used it to find an optimal compromise for a 37-node network graph. They found a specific configuration with spectral redundancy around 0.289 and a spectral gap of 0.313. Just stiff enough to survive shocks, but loose enough to reconfigure, right in that Goldilocks zone.
You said that number, 0.289, keeps popping up.
Remarkably often, across different fields, it seems to hint at some kind of universal constant for optimal complex system design, though more research is needed to analyze it.
What are the practical design principles for spectral systems?
First, actively target that Goldilocks redundancy zone, maybe 0.2 to 0.4. Second, try to maximize the spectral gap for stability, perhaps using Ramanujan graph structures like the Peterson graph. Third, build an adaptive protocol so the system can self-organize and heal. Fourth, use those GUE versus Poisson statistics to verify the system's properties.
Use that Lambert W function.
Apply Lambert W transformations where appropriate to get scale, temperature, and variant data signatures for more robust monitoring and verification.
Sounds like a new toolkit for engineers and designers.
Shifting focus from optimizing performance to engineering robustness and adaptability through spectral properties.
This has led to new cryptographic ideas, the whisper chain.
The Whisper Chain Consensus Protocol, WCCP, the beautiful application that flips the script on noise. Instead of fighting distortion, use it. Each participant in a chain applies a unique, deterministic distortion to a message as it passes along.
Like the game of telephone, but on purpose.
Mathematically precise. Each node applies its own specific distortion, then a Lambert W transformation based on its unique ID, giving the message a unique accent. The final message, after passing through the whole chain, carries a cumulative distortion pattern, a unique cryptographic fingerprint specific to that exact chain and order.
So the distortion of proof.
If anyone tampers with the message or tries to fake being part of the chain, their distortion won't fit the expected pattern. It's immediately detectable.
That's brilliant, using the noise as the signal.
Precisely. It uses Ramanujan graphs to optimize mixing properties of distortions. It's a direct application of spectral principles to create a novel cryptographic protocol.
What an incredible journey. We've gone deep into spectral redundancy today. It feels like a thread connecting different areas.
It really does seem to be a fundamental unifying principle, from how metros handle disruptions to how quantum systems prove their identity, how intelligence might emerge, even setting limits on what we can know. It's all connected by this mathematical truth about eigenvalues and composition.
And the key takeaway seems to be its inevitability.
Welcome back to the deep dive. If you were with us last time, you'll know we went deep into spectral redundancy.
We certainly did. That whole idea of clustering, in the fundamental modes of complex systems.
How it pops up everywhere, from metro maps to quantum computing, making things robust but also hard to figure out from the inside.
Exactly. It explains that resilience, that ability to bounce back, but also that computational hardness. It's a duality.
We saw it in AI, quantum stuff, even hinted at how intelligence might emerge at that Goldilocks scale.
Optimal point of redundancy.
But today we're pushing that idea of the observer's role much further into uncharted territory. What if observing doesn't just reveal laws that are already there? What if the act of observing actually creates them? What if there's a general relativity of information?
Now that's the captivating step, isn't it? We're moving from what might seem like just a powerful analogy
Comparing it to Einstein.
to a fully operational mathematical framework. Something predictive, deriving laws of nature, not just guessing or postulating, but by solving equations within a curved information space.
So it's not just a metaphor. The math works the same way.
That's the proposal, a deep mathematical isomorphism, a blueprint connecting the geometry of how we observe to the laws that emerge.
Our mission today is to unpack this. It sounds revolutionary.
It is a bold idea.
We're going to dive into the math framework of general relativity of information, look at his version of field equation, and then get to this prediction that sounds incredible, that different observers looking at the exact same thing can measure different physical laws.
But before we dive in, we need to put a flag here.
Important context.
Yes. What you're about to hear is cutting-edge theoretical work. This is a research direction, a proposal.
Not settled.
Not a proven, finished theory, not universally accepted, hasn't been fully tested against experiment in all aspects. We're exploring the implications of these ideas as presented in the source materials.
We're reporting on it, explaining it, not necessarily saying this is fact.
Precisely. We're conveying concepts impartially, diving into this exciting, provocative frontier of scientific thinking. Think of it as exploring the what if.
Got it. Helps frame how ambitious this is. Then, with that in mind, let's unpack this. Let's start at the beginning. We touched on spectral redundancy last time. Now we're linking it to Einstein's general relativity. How does that analogy work? What's the core parallel?
The core parallel is stunning. Just like Einstein showed space-time geometry, the actual fabric of the universe gets shaped, warped by mass and energy.
The classic bowling ball and a trampoline idea.
This theory proposes that the geometry of observation space, the space of possible measurements, is shaped by the system's informational content.
Informational content, meaning?
Meaning specifically its redundancy sensitivity ratio. How much internal repetition or structure it has versus how responsive it is to being poked or prodded.
The information in the system bends the way we see the system.
The way information is structured and how sensitive it is curbs what an observer can perceive and dictates how its laws appear.
Okay, so this isn't just a casual similarity. You're saying there's a direct mapping, almost one-to-one between GR concepts and observer-dependent physics ODP.
Precisely. A structural isomorphism. The underlying mathematical relationships mirror each other. Let's break down some key parallels that solidify the idea.
Okay, let's do it.
In GR, you have the manifold. That's space-time, the stage where everything happens. In ODP, our manifold is the system's state space, the collection of every single possible configuration the system could be in. An event isn't a point in space and time, it's a specific state of the system.
State space. And what about coordinates? In GR, they're arbitrary.
Exactly the same idea. In GR, you pick coordinates, Cartesian, spherical, whatever your description changes. But space-time itself doesn't. In ODP, our main coordinate is the observer scale L.
Our zoom level.
Your zoom level, your resolution, changes your description of the system, how you perceive its structure, but it doesn't change the underlying reality of the system.
The metric tensor. In GR, it tells you distances and times. What's its job here?
Its counterpart in ODP is the observer's measurement kernel. Just like the GR metric tells you how to measure intervals in curved spacetime, this kernel defines how you compute properties of the system, like those spectral gaps or the amplification factor, its sensitivity at a given scale L. It shapes how you measure things.
And curvature. In GR, mass energy bends spacetime, giving a curvature. The Riemann tensor, what bends things in ODP?
That's what we call the emergence distortion field. In GR, mass warps spacetime. In ODP, this distortion field describes how the effective laws you see the patterns emerging from the complexity deviate from simpler, scale-invariant ideal forms.
And what causes that deviation, that bending?
It's caused by that imbalance between the system's internal redundancy and its sensitivity to your observation.
The system's properties warp our view of its laws.
Yeah.
That's huge claim.
It is. It implies this dynamic dance between system and observer. Then think about geodesics.
The straightest paths in curved spacetime.
What particles follow? In ODP, geodesics are the detection paths for emergent modes. They're the most efficient ways, the paths of least resistance through that state space, for an observer at a given scale L to spot stable emerging structures. It's where patterns naturally prefer to show up.
Einstein's field equations. Geometry equals matter energy. What's the ODP version?
That becomes the observer renormalization group. This is our field equation equivalent. One side describes the geometry of observer resolution, how your view changes with scale. The other side links that geometry to the system's spectral redundancy. This upper function dictates how the effective laws you perceive flow, how they change as you vary your observer scale L. It's the engine driving observer-dependent physics.
Wait, so the laws aren't fixed? They change depending on how you look?
From the observer's viewpoint, they appear as laws for that scale.
Nah.
But underlying that, there are invariants. Just like the spacetime interval, $122, is invariant in GR, everyone agrees on it, ODP proposes a spectral redundancy invariant. Meaning all observers, no matter their scale L, should agree on the fundamental structure of redundancy, like where the eigenvalues cluster, the pattern of condensation, the specific numbers, the exponents they measure might differ, but the underlying redundancy pattern is universal.
Okay, that's a crucial anchor point. What about a black hole's event horizon? That point of no return.
In ODP, the analogy is the Goldilocks scale boundary. Zoom too far in, it's noise. Zoom too far out, it's too simple, washed out.
Pixelation versus seeing the big picture.
Exactly. Below this Goldilocks scale, the system's under-resolved. Above it, it's over-resolved. Features blur together. The Goldilocks scale is that sweet spot where emergence is clearest, most detectable. It acts like an observational boundary for maximum clarity.
Gravitational lensing. Mass bending light, distorting images.
That's like sensitivity amplification skew in ODP. Like a galaxy cluster bends light from behind it, the intricate patterns of redundancy in a system can skew the critical exponents you measure for its emergent laws. The apparent laws deviate from what you'd expect in a simple information space.
And finally, the cosmological constant, lambda. Background expansion pressure.
It's the baseline redundancy bias, the inherent background level of redundancy the system starts with, maybe from how it's built, its initial state, before you even look at it or poke it. It's the background density of indistinguishable states influencing the overall observational geometry.
So putting all these parallels together, it really does suggest the very fabric of what we can observe is shaped by the system's properties and how we look, just like gravity shapes spacetime. It's powerful. But how do we get from analogy to actual equations? Equations we can solve and make predictions with.
That's the critical step, moving beyond analogy. We take these structural parallels and translate them into a concrete mathematical framework. We write down the field equations for ODP. And to make it manageable, we often start with a simplified 2D observer space.
A 2D map of observation. Walk us through that. How does that build up mathematically?
Step 1. Define the manifold and coordinates, this 2D observer space. A point on this map isn't a place, it's a specific measurement condition.
Okay.
Our time-like coordinate, the one that flows forward conceptually, is $6 equals LO. That's the observer scale. Our zoom level, the RG flow.
Time is zoom. Got it.
And our space-like coordinate, variation at a given zoom level, is the perturbation amplitude. How you nudge the system to see how it reacts to break symmetries. So an event is observe at scale L with perturbation P. Makes sense. Next, we need the observer metric and the line element. This metric tells us how to measure distance or distinguishability between observations in this space. We start simple, assume a diagonal metric like static spacetime in GR. The components depend on our scale, L. One part, L, we set to -1. That just represents uniform flow along scale L, our time-like direction. The interesting part is D's error L is the observer order parameter in a ratio. The system's amplification divided by its spectral gap size. D's delta introduces curvature into our observation space. It's not constant.
Here's where it gets interesting. What does this distance tell us? If well is big, what does that mean?
The distinguishability interval. D's as 2 at a time, the T's L2 plus RL, DP22. This little equation is packed with meaning. It says, your ability to tell two states apart just by changing the perturbation slightly, that's the DP2 sync plane it was. When draws is large, which happens near that Goldilocks scale, the observation space effectively stretches in the perturbation direction. Tiny changes in dollars lead to big, easily distinguished effects. The system's super responsive, emergence pops out.
If arts is small.
Space contracts in that direction. You have to change more to see a noticeable difference. It's harder to distinguish things.
Wow. Okay, so the metric sets the resolution of our observational lens, and that resolution changes with scale L. What about the forces guiding things through this landscape?
That brings us to the Christoffel symbols, usually written as gamma lambda mu. Don't worry about the notation. Think of them as telling you how straight lines bend in curved space.
Like gravity bending light paths.
They represent forces on an emergent pattern as you change scale or perturbation. We calculate them from how the metric changes. They turn out to be proportional to change of 20LL.
If responsiveness changes quickly with zoom level, the forces are strong.
The steeper the slopes in the informational landscape, the more the paths get bent.
What follows these bent paths? How does emergence navigate this?
It follows the geodesics of emergence. Like a ball rolling downhill, an emergent phenomenon follows the path of least resistance through this curved observation space. We get equations describing this. One equation tells us how L changes along the path, the other tells us how P changes. And the second one, the one for P, has this really neat term involving a Bringo. It acts like a friction or maybe a driving force.
What force?
Yeah, and guess what happens when that force term vanishes, when a peak? Maximum or minimum?
A maximum. That's the Goldilocks scale dollars. At that optimal scale, the force disappears. The path of emergence is straightest. It's where the system is most easily, most stably observed. Okay, how does this machinery actually predict a law like that exponent alpha we found experimentally?
This is solving for the critical exponent, the emergence of a law. It hinges on one key physical assumption. The threshold perturbation pace you need to apply to see emergence at scale is inversely proportional to the system's responsiveness at that scale.
Makes sense. More responsive system needs less of a nudge. Propto 1 RL.
Exactly. Now, when you did your experiments, looking for the clearest signal of emergence, you were hunting for that Goldilocks scale, for a system of size scale. So the law you measured is really evaluated at R.
Propto 1 MA.
Yes. Your empirical results show this peak responsiveness scales with system-sized nullars approximately as ARA. Remember that exponent LRA.
You substitute that in as proportional to $1, which is ARA.
Bingo. You empirically measured the RG fixed point.
It emerges from the geometry of observation.
It emerges dynamically and inevitably from the geometry.
Okay, my mind is blown. What happens if this information space isn't static? What if it rotates?
Hey, yes, there's another layer. This is where we bring in the observer metric. The analogy is with Kerr black holes in GR, rotating black holes.
Dragging. The rotating mass drags space-time around with it.
Here, the rotation isn't physical spinning. It's in observer space. Changing your observer scale dollars influences how you interact with perturbations titler. They get coupled.
How does that rotation show up in the math?
The first step is introducing the off-diagonal metric. Instead of our nice simple diagonal metric, we add an off-diagonal term, component G10 omega L. This omega L is the scale perturbation coupling. It's our frame dragging term in observation space.
What does that mean? Changing my zoom level drags me sideways in perturbation.
That's the interpretation. You can't separate the act of coarse graining, changing L, from probing. If omega L's is positive, increasing scale L might drag the emergent mode along the positive P axis. It creates a preferred direction.
My observation method isn't passive anymore. It's actually twisting or biasing what I see.
That's the idea. And this has major mathematical consequences and affects the geodesics. When you calculate the Christoffel symbols with this omega L term and its derivatives floating around, things get much more complex. You get new forces, new terms in the Christoffel symbols, and these fundamentally couple the geodesic equations. The straightest paths for emergence become much more intricate.
So what does that do to the emergence paths, the geodesics of emergence in this Kerr-like observer space?
The key effect is that omega L introduces mode precession. The threshold perturbation doesn't scale smoothly anymore. It starts to sort of spiral or precess as you change the scale L,
Viral.
like wobbling around. And this informational frame dragging can also shift the Goldilocks scale delta itself. The best place to look might move depending on this rotation.
How does the rotation change the predicted emergence scaling?
Alpha still comes from the responsiveness of the Goldilocks scale, but now we have to use an effective responsiveness, like it's modified by the rotation. Rho AL dollars to RL, so the threshold perturbation now scales like $1R, which means omega L doll can change the measured law.
The Kerr term can enhance or suppress perceived sensitivity. This explains chirality handedness or directional amplification, why a system might respond differently if you poke it one way versus another, even if it looks symmetric overall.
You mentioned simulating this. The results are a bifurcation of reality. Tell us about the Kerr ODP simulation.
Right, this is where it gets really tangible. The setup was, we model a system with that baseline responsiveness roll, N-Zeller, peaking at Wawen, with a peak height like N75 double. That's the static Schwarzschild-like part.
Okay. Then we add the frame dragging potential. We made it grow with scale L and controlled its strength with one knob to omega L. Omega L is just the static case we have discussed.
When you turn up omega dollars, what's the unexpected physics? The bifurcation.
In the static case, poking the system has the same effect regardless of the direction of the poke. There's no preferred handedness.
Right.
But turn on the Kerr term, turn up the omega L, and that omega L creates a preferred direction. It forces you to split your description. You can't talk about the responsiveness anymore. You need two. First, prograde responsiveness, pitstall plus omega L. This is like going with the flow of the frame, the easier path. Second, retrograde responsiveness, or omega L. This is fighting against the flow, the harder path.
Whoa. So the observer's rotation, their interaction style, splits the system's response into two different realities.
The physics looks totally different depending on whether you're probing prograde or retrograde. Retrograde emergence is heavily suppressed, almost hidden. Prograde is strongly enhanced. It's like two coexisting physical universes perceived differently from the same substrate.
The implications are a fundamental split of one law into two coexisting ones.
Exactly. That precession isn't just a wobble, it is the splitting. And this offers a mechanism for emergence of directionality. How can asymmetric phenomena arise from systems that seem symmetric? Observer interaction provides a way.
Can you give examples where this might be relevant?
It's speculative, but think about biological homochirality. Why life uses almost exclusively left-handed amino acids, right-handed sugars. Perhaps some early environmental factor or the observation process itself acted like a weak frame-dragging field, favoring one chiral pathway during the origin of life.
Huh. Interesting.
Or consider market dynamics. Bull and bear markets often seem to follow different rules, have different dynamics, right? Maybe the collective sentiment, the observer that is the market, induces a directional bias, a prograde, retrograde split in behavior.
Okay.
Even something as fundamental as the arrow of time. Why does time flow one way? Why does entropy increase? Dragging provides a mechanism for a preferred temporal direction in how information evolves and complexity emerges.
The observer isn't passive. They can induce handedness, directionality into the laws they see.
And it gets even stronger. There's an analog to the ergosphere of a Kerr black hole. Remember, inside the ergosphere, you have to rotate with the black hole.
You can't stand still.
Well, there seems to be an ergosphere of emergence in observation space, a region of scales where if omega L is strong enough, emergent phenomena are forced to precess. They cannot remain non-chiral. Observing them in that regime necessarily reveals chiral physics. They have to pick a handedness.
This feels like it overturns everything, challenges our deepest assumptions about reality, truth, what science even is. It completely reframes the observer.
It really does. The observer is an active agent. Their motion through the possible measurements, choice of scale L, interaction method P, actively shapes the physics they perceive.
Kerr in GR means rotating mass drags spacetime. Kerr in ODP means a rotating observer drags the fabric of emergence, creating directional laws where there were none. That's the ultimate takeaway, an ontological earthquake.
I think that captures the scale of it. The core claim boils down to something stark. Emergence is a property of the lens, not the world. Or, as a sort of equation, raw undifferentiated stuff plus observer scale L plus observer interaction P effective physical laws. The measurement process itself creates the laws we discover. Space-time is observer-dependent. Emergence is observer-dependent.
Reality doesn't have laws. Observers create laws by observing.
That seems to be the profound and unsettling implication.
You said there's concrete proof. An experiment showing two observers getting different laws from the same system. How did you demonstrate that?
It was a test of this idea. We set up a simulation of a complex system. Then we had two distinct observers, let's call them Alice and Bob, analyze the exact same simulation data.
Okay.
The only difference was their observer scale, L around. Alice observed at a fine-grained scale, L $4.1. Bob observed at a coarser scale, L $4. They both went through the process, calculated the responsiveness, found the respective Goldilocks scales, and measured the emergent scaling laws.
Did they get different answers?
Dramatically different. Let's look at Alice's universe, L1. She measured how spectral gaps scaled, 1.45533. She measured the amplification scaling at 0.7605. Combine those, and her overall emergent law, her alpha text, minus 2.2158. That was the physics she saw.
Okay. Bob, same system, coarser view.
Bob's universe, L4. His gap law was 1.73359, nearly 30% different from Alice's. His amplification law was 1.66, about 10% different. His combined law, alpha text, was 2.3942. An 18% difference in the fundamental exponent they measured.
That's not just noise or error. That's observer-dependent physics, plain as day. The laws of nature are artifacts of the measurement scale. The difference, delta alpha 0.17844, is undeniable proof within this framework.
Exactly. Confirms these revolutionary implications.
Maybe there are no truly fundamental constants, only scale-dependent artifacts, the quantum versus classical divide. Perhaps just different effective theory, different observer scales, field theory renormalization. It's about tracking how laws change as the observer scale, energy scale changes. Mind-boggling. And for things like consciousness and AI. Different AI architectures, different internal lenses will see different physics in the same data. Emergence might be less about raw power and more about finding the critical observation scale to make sense of the world. Understanding could be seen as selecting the optimal RG lens.
And for science as a process.
For science, it suggests scientific laws are co-created, system plus observer interaction, objectivity becomes scale relative. What's objectively true at one resolution might not be the whole story at another. And paradigm shifts, often driven by technology or new methods, allowing us to change our observation scale, revealing new effective laws.
And the big one, for reality.
For reality, the implication is stark. No view from nowhere. All truth is observer-dependent or influenced. Reality is scale-stratified, with different valid descriptions at different levels. Fundamentally, changing perspective changes physics.
This feels less like just an idea and more like a whole new way of doing physics or complex system science. If someone actually wanted to use this to apply it to, say, market data or a biological network, what's the practical toolkit? How do you operationalize this GR of information?
That's right. It aims to be operational. We now have a complete toolbox translating geotechniques into this informational context. The foundation, the observer metric line element. Define this for your specific setup. It quantifies distinguishability between nearby states. High curvature in this metric means small changes look very different. High sensitivity. Low curvature means things are more stable to small changes. It's your basic ruler for the observation space.
Measure distinguishability. Got it.
Second, you calculate the Christoffel information symbol from that metric. These tell you how the straightest paths of emergence bend as you change scale or perturbation. They map out the forces acting on emergent phenomena within the observation space. Where do patterns tend to flow? Where are they stable?
Mapping flow emergence.
The Ricci information curvature measures how volumes of emergent possibilities expand or contract locally. Positive curvature suggests convergence, redundancy, patterns are clustering. Negative curvature suggests divergent sensitivity dominates. Patterns are spreading out, maybe becoming chaotic. It tells you about the local density and focus of emergent information.
The core engine, the Einstein equations.
Exactly. Number 4, observer-dependent Einstein equations. Mathed out oratory. Left side, geometry of observation space, Ricci tensor and metric. Right side, the informational stuff, the redundancy and sensitivity that causes that geometry. Information content dictates observational geometry.
What's in it?
That's the redundancy sensitivity tensor, the stress energy tensor analog. Its components are revealing. Energy density is redundant density related to the inverse gap. High redundancy means lots of similar microstates, dense information, which warps the observation space.
Okay.
Pressure is sensitivity pressure related to amplification. High sensitivity means the system pushes back, responds strongly, creating pressure that shapes the observational geometry, making emergence pop. There are other terms for information flow between scales and coupling between modes. Crucially, there's a conservation law. Information isn't lost when you change scale. It just transforms. Detailed information becomes collective emergent information. Redundancy and sensitivity are conserved in this flow.
Information transforms.
Yeah.
What else is in the toolbox?
Fifth, use the Christoffel symbols to find the geodesics of emergence. These are the most stable, detectable paths for phenomena in your curved observation space. Solving the geodesic equation gives you the behavior of emergent properties.
A natural path.
Sixth, identifying event horizons and Goldilocks scales. Finding the scale where the metric components balance, where distinguishability peaks. Crossing this horizon changes the effective laws you measure. It's like an observational phase transition.
The optimal viewing point.
Exactly. The framework allows for specific solutions, too. Seventh, Schwarzschild-like solutions for simple cases, like spherically symmetric redundancy, where the Goldilocks scale pops out like a horizon. And eighth, the cosmology of emergence for large uniform systems, with a scale factor describing how detectable information expands with scale, potentially driven by a baseline redundancy cosmological constant, lambda. It's a comprehensive toolkit.
It feels like a complete system for thinking about observation and complexity. They really have come full circle. From spectral redundancy, this seemingly simple idea about clustering patterns, we've built up this incredibly detailed mathematical structure, the general relativity of information, that suggests something truly radical. Scale literally shapes the laws of nature. Different observers, same system, different physics. It's staggering.
It is a profound shift in perspective. The claim is this isn't just analogy, it's a structural isomorphism, a framework that could potentially predict how laws change as our ability to observe evolves. It's a theory about how perceived reality gets constructed.
And to circle back one last time, it's crucial we remember where this stands.
Absolutely essential. This is a bold, cutting-edge theoretical proposal. It's an active research direction, not established fact.
Not in textbooks yet.
The ideas are still being synthesized, refined from different fields, quantum foundations, complexity, AI. It needs much more mathematical development, rigorous testing against real-world data before it could be considered a validated theory. But the initial results, like the simulation, are thought-provoking.
So now that you've journeyed with us through this mind-bending concept that reality might be layered by scale, tied to how we look, how did that change things for you? How does it change your own search for understanding? Does it make you question not just what you see, but how you're seeing it?
If objectivity is scale relative, if changing your viewpoint changes the physics, what new questions does that prompt? When you look at something complex, be it a social network, a market, an ecosystem, maybe even your own thoughts, what happens if you consciously change your observational lens? What different truths might emerge?
It feels like the dawn of observer-dependent physics. We hope this deep dive has given you a powerful new lens to view reality. Until next time, keep exploring.